students, now I am going to derive continuity equation based on, yesterday we already derived continuity equation, okay, that is control volume approach. Okay, now this is continuity equation based on stream tubes. Okay, so there are two ways by which continuity equation we can derive based on that is control volume approach that we have already derived yesterday. Now I am going to derive continuity equation based on stream tube concept. So see, stream tube concepts based on streamlines, okay, like this. So see, these are the streamlines, okay, and this is a stream tube of length ds. So consider a stream tube. Consider a stream tube of length ds. Okay, now this is entry, okay, and this is exit. So that is mass at entry will be equal to rho a b, continuity equation, okay, that is m dot. Mass at entry is rho a b, okay. Now mass at outlet, or it is called exit, okay. So mass at outlet will be equal to, see, rho a b plus d by ds into rho a b into ds. Okay, now mass accumulated within body will be equal to that mass, see, that is mass at entry minus mass at exit, okay. So mass at entry is rho a b minus, this one will be rho a b plus d by ds into rho a b into ds, okay. So this term will get cancelled. So mass that is accumulated within the body actually will be equal to minus d by ds into rho a b into ds, okay. Now rate of change of mass at entry and exit, that is will be equal to, what will be there? That will be d by dt into rho into a into ds, okay. So principle of mass conservation states that mass can neither be created nor be destroyed, okay. So this equation, this is equation 1 and this is equation 2 based on conservation of mass will be equal to, these two, equation 1 and 2 will be the same, okay. So that way we can write like this, d by dt into rho a ds will be equal to minus d by ds into rho ab into ds. So ds will get cancelled. Okay. Now see here, this term for steady flow, d by dt into rho a is equal to 0. So what we will get? D by ds into rho ab is equal to 0. See, it is for compressible fluid, so this can be cancelled out. So d by ds will be, if you integrating between limit 1 to 2, so this will give us integrating with respect to ds a1 v1 is equal to a2 v2. This is continuity equation for one dimensional, remember, based on a stream tube. In the last lecture, we have already derived continuity equation based on control volume approach. Okay. In this session, we have derived the relation, same relation, that is continuity equation a1 v1 is equal to a2 v2. That equation based on a stream tube concept. So let us consider a stream tube of length ds. Mass at entry is rho ab. Mass at outlet is rho ab plus d by ds into rho ab into ds. So mass accumulated within the body will be equal to mass at entry minus mass at exit. So this is mass at entry and this is mass at exit. Okay. So rho ab minus this mass at exit is rho ab plus d by ds into rho ab into ds. Okay, so this term will get cancelled and there will be minus d by ds into rho ab ds. Okay, and the rate of change of mass at entry and exit will be d by dt, time rate. Okay, rho a, here density is a into ds. Okay, so mass density is rho and we want rate of change of mass. So a into ds based on mass conservation of energy. Equation 1 and 2 will be the same. So d by dt into rho a into ds will be equal to minus d by ds rho ab into ds will get cancelled. For a steady flow, we can consider this as a 0. So this will be just positive, so that will d by ds into rho ab. Okay, so that is 0, and if you integrate between limits 2 to 1, it will be a1 v1 is equal to a2 v2. This is continuity equation, and based on stream tube concept. Okay, so what we have derived, that is for one dimensional. Okay, that is for continuity equation for one dimensional flow. And in next lecture I am going to derive continuity equation or differential continuity equation for three dimensional, that means x coordinate, y coordinate and z coordinate also. Okay, so we will derive that relation in next lecture. Thank you.